What if the Earth's deepest secrets were whispering to us, waiting to be heard? Prepare to journey into the planet's core, uncovering geological discoveries so profound they'll change how you see our world. This isn't just about rocks. It's about the hidden narratives of our planet's formation, offering a tranquil escape as you drift into knowledge. 1. The discovery of quasicrystals in nature. Imagine discovering something in nature that scientists once believed could never exist outside of laboratory conditions. This extraordinary revelation unfolded in the remote wilderness of Russia's Chukotka Peninsula, where researchers examining meteorite fragments made a discovery that fundamentally challenged our understanding of how matter organizes itself in the natural world. Quasicrystals represent a fascinating middle ground between the perfect order of crystals and the complete randomness of glass. Think of traditional crystals as wallpaper patterns that repeat endlessly in predictable ways. Now imagine a pattern that appears ordered and structured, yet never quite repeats itself exactly the same way twice. This is the essence of quasicrystalline structure, where atoms arrange themselves according to mathematical principles that create beautiful, complex patterns without true periodicity. The discovery began when scientists noticed unusual metallic grains within a meteorite sample that had fallen to Earth approximately 15,000 years ago. These tiny fragments, no larger than grains of sand, displayed atomic arrangements that violated fundamental rules of crystallography that had stood unchallenged for centuries. The atoms within these natural quasicrystals follow mathematical relationships based on the golden ratio, creating five-fold symmetries that traditional crystal structures cannot accommodate. What makes this discovery particularly remarkable is how these quasicrystals formed. They likely crystallized under extreme conditions of temperature and pressure during the early formation of our solar system, perhaps within the collision of asteroid bodies or during other catastrophic cosmic events. The specific mineral, called icosahedrite, contains aluminum, copper, and iron arranged in patterns that display perfect icosahedral symmetry. This discovery proved that nature could create these supposedly impossible structures. 2. Deep groundwater systems millions of years old. Beneath our feet lies a hidden ocean of water that has remained trapped in darkness for millions of years, completely isolated from the surface world we know. These ancient groundwater systems represent some of the oldest water on Earth, preserved in deep rock formations like liquid time capsules that tell stories of climates and environments from ages long past. To understand these deep water systems, picture Earth's crust as a vast underground apartment building with countless floors extending downward for miles. Each level contains different types of rock with varying abilities to store and transmit water. The deeper we go, the older and more isolated these water reservoirs become. Some of these deep aquifers contain water that fell as rain during the time when dinosaurs roamed the Earth, slowly filtering down through rock layers over geological timescales. Scientists have discovered groundwater in Canada's Kidd Creek mine that is approximately 2 billion years old, making it older than complex life on Earth. This ancient water moves through the rock at rates so slow that a single drop might travel only a few meters in a million years. The water itself tells remarkable stories through its chemical composition, containing dissolved minerals and gases that provide direct evidence of ancient atmospheric conditions. These deep water systems often support unique ecosystems of microorganisms that have evolved in complete isolation from the surface world. These ancient bacteria derive energy not from sunlight, but from chemical reactions with the surrounding rock, creating self-sustaining communities that have persisted in absolute darkness for millions of years. Understanding these systems helps scientists explore possibilities for life in extreme environments on other planets, while providing crucial insights into water resources. 3. The Great Unconformity's missing billion years. Across the world's continents lies one of geology's greatest mysteries, a missing chapter in Earth's story that spans nearly 1 billion years of our planet's history. This phenomenon, known as the Great Unconformity, represents a massive gap in the geological record where rocks that should document crucial periods of Earth's development simply do not exist or have been completely erased from the stone archive of deep time. Imagine opening a history book only to discover that several hundred pages, covering critical periods, have been torn out completely. This is essentially what geologists encounter when they examine rock sequences around the world. In location after location, they find ancient rocks from around 1 billion years ago, sitting directly beneath much younger rocks from around 500 million years ago, with virtually nothing preserved in between. This missing interval represents one of the most significant periods in Earth's development. The Great Unconformity likely formed through a combination of massive erosion and tectonic processes during the breakup of an ancient supercontinent called Rodinia. As this enormous landmass began to split apart, vast mountain ranges were uplifted and then gradually worn down by hundreds of millions of years of weathering and erosion. Rivers, glaciers, and chemical weathering systematically removed layer after layer of rock, carrying the sediments into ancient ocean basins where they were buried and lost to the geological record. Recent research suggests that this period of intense erosion may have played a crucial role in triggering the Cambrian explosion of life. By releasing vast quantities of nutrients into the oceans, the erosion exposed fresh minerals to chemical weathering, which released phosphorus and other essential elements that marine organisms needed to build shells and bones. This missing billion years thus represents not just an absence, but a critical transformation.
4. Coral growth bands as seasonal climate indicators deep beneath tropical waters. Coral polyps construct their calcium carbonate skeletons with remarkable precision, creating natural archives of environmental conditions that stretch back centuries. These living time machines record seasonal variations in temperature, ocean chemistry, and rainfall patterns through subtle changes in their growth bands. Much like tree rings document terrestrial climate history, understanding how corals encode environmental information helps scientists reconstruct past climate conditions and predict future changes in our warming world. Think of coral growth as nature's own seasonal diary. During warmer months when conditions favor rapid growth, corals deposit wider bands of skeleton material. Cooler seasons produce narrower bands, creating annual patterns that scientists can count and measure with extraordinary precision. But the story goes much deeper than simple growth rates. The chemical composition of each band reflects the exact temperature and chemistry of the seawater when that particular layer formed. Oxygen isotopes within the coral skeleton provide the most reliable temperature records. When seawater is warmer, corals incorporate slightly different ratios of oxygen isotopes into their calcium carbonate structure. These minute chemical signatures allow researchers to reconstruct sea surface temperatures with remarkable accuracy, often within a few tenths of a degree. Additionally, trace elements like strontium and magnesium vary with temperature and provide independent confirmation of thermal conditions. What makes coral records particularly valuable is their ability to capture short-term climate variability that other archives miss. While ice cores and lake sediments provide annual or decadal resolution, coral bands can reveal monthly or even weekly environmental changes. Some coral colonies have been growing continuously for over 400 years, creating uninterrupted climate records that predate human instrumental measurements by centuries. These archives have revealed previously unknown patterns of tropical climate variability and helped scientists understand how ocean-atmosphere interactions influence weather patterns across the Pacific and Atlantic basins, providing crucial context for modern climate change. 5. Ultra-low velocity zones at the core mantle boundary. Nearly 3,000 kilometers beneath our feet, at the boundary between Earth's molten iron core and solid rocky mantle, seismic waves encounter mysterious regions where their velocity drops dramatically. These ultra-low velocity zones represent one of the most enigmatic features of our planet's deep interior, where seismic waves slow down by up to 50% compared to surrounding mantle rock. Understanding these zones helps scientists piece together the complex thermal and chemical processes occurring at the most extreme boundary within our planet. Imagine sound waves traveling through different materials in your house. They move quickly through solid wood floors, more slowly through soft carpet, and differently still through water or air. Seismic waves behave similarly as they journey through Earth's interior, and their changing velocities reveal the properties of materials they encounter. When these waves reach the core mantle boundary, some encounter regions where their speed drops so dramatically that scientists initially questioned whether their instruments were malfunctioning. These ultra-low velocity zones likely represent regions where the mantle rock has partially melted due to heat flowing from the molten iron core below. The temperature at this depth reaches approximately 4,000 degrees Celsius, hot enough to begin melting even the high-pressure minerals that normally remain solid throughout the mantle. This partial melting creates a complex mixture of solid crystals suspended in liquid rock, dramatically altering the mechanical properties and seismic wave velocities Recent research suggests these zones may play crucial roles in mantle convection and the generation of hotspot volcanism that creates chains of volcanic islands like Hawaii. The partially molten material in these zones is less dense than surrounding solid rock, causing it to rise slowly through the mantle over millions of years. This upwelling eventually reaches the surface as volcanic hotspots, demonstrating how processes occurring at Earth's deepest accessible boundary influence surface geology and create some of our planet's most spectacular volcanic features.
6. The formation of giant crystal caves. Hidden beneath the Chihuahuan Desert of Mexico lies one of Earth's most extraordinary underground chambers, the Cave of Crystals, where selenite crystals grow to enormous proportions in conditions that seem almost alien to surface dwellers. Some of these translucent giants stretch over 11 meters in length and weigh as much as 55 tons, creating a surreal landscape of crystalline pillars and beams that challenge our understanding of how minerals can grow in natural environments. These caves represent perfect laboratories for studying crystal formation under extreme conditions. To understand how such massive crystals formed, we must journey back approximately 26 million years when this region lay beneath ancient seas. Hydrothermal fluids, heated by magma chambers deep below, circulated through limestone bedrock, gradually dissolving the rock and creating underground caverns. As these hot, mineral-rich waters cooled and became supersaturated with calcium sulfate, the conditions became perfect for selenite crystal nucleation and growth. The key to growing such enormous crystals lies in maintaining incredibly stable conditions over vast periods of time. Unlike surface environments where temperature and chemical conditions fluctuate constantly, these deep caves maintained nearly constant temperatures around 58 degrees Celsius for hundreds of thousands of years. The groundwater remained saturated with dissolved calcium and sulfate ions, providing a continuous supply of building materials for crystal growth. What makes these crystals particularly remarkable is their exceptional clarity and size. Selenite forms when calcium sulfate crystallizes from solution under relatively low temperature conditions. The slow, steady growth allowed atoms to arrange themselves in nearly perfect crystalline lattice, creating crystals with optical clarity rivaling manufactured glass. The extreme heat and humidity in these caves, reaching 100% humidity at temperatures that approached the limits of human survival, created conditions where only the most perfectly formed crystals could survive and continue growing, resulting in these spectacular mineral cathedrals hidden deep within Earth's crust. 7. Turbidite systems and deep-sea fan formation. Imagine standing at the edge of an underwater cliff thousands of meters below the ocean's surface, watching as massive avalanches of sediment cascade down the continental slope in thundering underwater landslides. These turbidity currents represent some of the most powerful erosional forces on our planet, carving submarine canyons deeper than the Grand Canyon, and depositing vast fan-shaped accumulations of sediment across the abyssal ocean floor. Understanding these systems helps us appreciate how continents gradually shed their weathered remains into the deep sea over geological time. Think of turbidity currents as underwater rivers of mud and sand that flow with tremendous speed and power down the continental slope. When earthquakes, storms, or simple gravitational instability triggered the collapse of sediment accumulated on the continental shelf, enormous volumes of water and debris begin flowing downslope under the influence of gravity. These dense, sediment-laden currents can travel at speeds exceeding 100 kilometers per hour, carrying everything from fine clay particles to massive boulders hundreds of kilometers across the ocean floor. As these currents lose energy in the deeper, flatter regions of the ocean basin, they begin depositing their sedimentary load in distinctive sequences called turbidites. Each turbidite represents a single flow event, with coarser materials settling first and finer particles depositing on top, creating graded beds that tell the story of each underwater avalanche. Over millions of years, countless turbidity currents build enormous submarine fans that can cover areas larger than entire countries. These deep-sea fans preserve detailed records of continental erosion, climate change, and tectonic activity. Scientists studying turbidite sequences can reconstruct ancient patterns of rainfall, mountain building, and sea level fluctuations by analyzing the composition and timing of sediment delivery to the deep ocean. Within some of the oldest rocks on Earth lie tiny crystal time capsules that survived from our planet's most violent and mysterious early period. These microscopic zircon crystals, no larger than grains of sand, formed during the Hadean Eon, more than 4 billion years ago, when Earth was a hellish world of molten rock, asteroid bombardments, and an atmosphere toxic to any life we know today. These resilient minerals represent our only direct physical evidence from this crucial period, when our planet was transforming from a ball of cosmic debris into a world capable of supporting oceans and eventually life itself. Picture Earth during its infancy as a glowing sphere of molten magma, constantly pelted by asteroids and comets in a cosmic shooting gallery called the Late Heavy Bombardment. The surface temperature exceeded 1000 degrees Celsius, and the atmosphere consisted primarily of water vapor, carbon dioxide, and other volcanic gases. In this seemingly impossible environment, zircon crystals began forming within the first granitic rocks as they cooled and solidified from the global magma ocean. Zircon possesses remarkable properties that allow it to survive almost any geological process our planet can produce. Its crystal structure incorporates uranium atoms that decay radioactively at known rates, providing precise age dates for when the crystals formed. Additionally, zircon is nearly indestructible, resisting melting, chemical alteration, and mechanical weathering that would destroy most other minerals. This durability allows Hadean zircons to survive billions of years of recycling through the rock cycle. Chemical analysis of these ancient crystals reveals surprising information about early Earth conditions, rather than the completely molten hellscape scientists once imagined. Some Hadean zircons contain chemical signatures, suggesting that liquid water oceans may have existed much earlier than previously thought, perhaps within a few 100 million years of Earth's formation. 9. Piezoelectric effects in deep crustal minerals. Deep within the continental crust, certain minerals possess the remarkable ability to generate electrical charges when subjected to mechanical stress, creating natural electrical phenomena that may influence everything from earthquake processes to the migration of subsurface fluids. This piezoelectric effect transforms the mechanical energy of tectonic forces into electrical energy, essentially turning portions of Earth's crust into vast natural batteries that charge and discharge in response to geological processes. Understanding these electrical properties helps scientists explore new connections between mechanical deformation and the chemical and physical processes occurring in the deep Earth. To understand piezoelectricity, imagine squeezing a crystal and watching it produce a small electrical current in response to the mechanical pressure. This phenomenon occurs because the crystal structure of certain minerals contains positive and negative charges arranged in precise geometric patterns. When mechanical stress distorts the crystal lattice, it displaces these charges slightly, creating electrical dipoles and generating measurable electrical potentials across the mineral grain. Quartz represents the most common piezoelectric mineral in Earth's crust, and its electrical properties become particularly important in high-stress environments like active fault zones and areas of ongoing mountain building. When tectonic forces compress quartz-rich rocks, the resulting electrical charges can influence the behavior of groundwater, alter chemical reaction rates, and potentially affect the nucleation and propagation of earthquake ruptures. Some researchers suggest that piezoelectric effects might even contribute to earthquake precursor phenomena by generating electrical signals before major fault movements. Recent research has revealed that piezoelectric effects in deep crustal rocks may play important roles in metamorphic processes, by creating local electrical fields that influence the movement of ions and the growth of new minerals. These electrical phenomena represent yet another example of how mechanical, chemical, and electrical processes interact in complex ways throughout Earth's crust. 10. Deep lake sediment, climate archives. Hidden beneath the tranquil waters of lakes around the world lie some of Earth's most detailed records of climate history, preserved in the fine layers of sediment that accumulate year after year on lake bottoms. These underwater archives capture seasonal variations in rainfall, temperature, and ecosystem changes with remarkable precision, creating natural libraries that document environmental conditions spanning thousands or even millions of years. Understanding how lakes preserve climate information helps scientists reconstruct past environmental conditions and provides crucial context for understanding modern climate change within the broader framework of natural variability. Think of lake sediments as pages in a vast book of environmental history, with each thin layer representing a single year of deposition. During spring snowmelt and summer rainstorms, rivers carry eroded soil, pollen grains, and organic matter into lakes, where these materials settle slowly through the water column and accumulate on the bottom. In winter, when biological activity slows and fewer sediments enter the lake, different types of materials dominate the settling particles, creating distinct seasonal layers called varves. The beauty of lake sediment records lies in their incredible detail and continuity. Unlike marine sediments that can be disturbed by deep ocean currents, or terrestrial deposits that may be eroded by surface processes, lake bottom sediments often remain undisturbed for millennia. Each annual layer contains microscopic fossils of algae and other organisms that lived in the lake, pollen grains blown in from surrounding forests, and chemical signatures that reflect the temperature and chemistry of the lake water when the sediments were deposited. Scientists extract these sediment archives using specialized coring equipment that preserves the delicate layering structure. Laboratory analysis reveals detailed records of past droughts, floods, volcanic eruptions, and ecosystem changes that provide essential baselines for understanding how natural systems respond to environmental stress, helping us better prepare for future climate challenges. 11. Serpentinization reactions in ocean floor, spreading centers deep beneath the ocean waves, along the volcanic mountain chains that mark where tectonic plates pull apart. An extraordinary chemical transformation occurs that may hold keys to understanding how life began on Earth. This process, called serpentinization, happens when seawater interacts with newly formed oceanic crust, triggering chemical reactions that fundamentally alter the mineral composition of the rock, while producing hydrogen gas and creating alkaline conditions that could support primitive forms of life. These reactions represent some of the most important chemical processes occurring on our planet, linking the geological engine of plate tectonics with the chemical foundations necessary for biological systems. Picture the mid-ocean ridges as underwater volcanic mountain ranges where molten rock continuously emerges from Earth's interior to form new oceanic crust. As this hot, fresh rock comes into contact with cold seawater, intense chemical reactions begin immediately. The primary minerals in the newly formed oceanic crust, especially olivine and pyroxene, contain iron and magnesium in chemical forms that readily react with water molecules under the high temperature, high-pressure conditions found at depth beneath the seafloor. During serpentinization, water molecules break apart and recombine with the rock minerals to form new hydrated minerals called serpentine, which gives this process its name. This transformation dramatically changes the physical and chemical properties of the oceanic crust, making it less dense and more prone to chemical weathering. More importantly, for understanding early life, these reactions produce hydrogen gas as a byproduct, creating a potential energy source for chemosynthetic organisms that can derive energy from chemical reactions rather than sunlight. The alkaline, hydrogen-rich environments created by serpentinization reactions may closely resemble the conditions where life first emerged on early Earth, making modern serpentinizing systems natural laboratories for studying how biological processes might arise from purely geological chemical reactions. 12. The Wilson cycle and supercontinent assembly. Throughout Earth's history, continents have engaged in a slow-motion dance of assembly and breakup that spans hundreds of millions of years, driven by the restless motion of tectonic plates beneath their feet. This grand cyclical process, known as the Wilson cycle after the Canadian geophysicist who first described it, explains how supercontinents form, mature, and eventually fragment to begin the cycle anew. Understanding this fundamental rhythm of continental motion helps scientists reconstruct the geographic history of our planet and predict how the continents might be arranged millions of years in the future. Imagine watching a time-lapse movie of Earth's surface spanning several 100 million years, and you would witness continents slowly drifting across the globe like enormous rafts on a turbulent sea. The Wilson cycle describes this motion as a series of predictable stages that repeat throughout geological time. The cycle begins when tensional forces start to stretch and thin the continental crust, eventually creating rift valleys like the modern East African rift, where the continent begins to split apart. As rifting continues, the continental fragments separate and new oceanic crust forms between them, creating expanding ocean basins. This stage can persist for hundreds of millions of years as the ocean continues to widen, carrying the continental fragments farther apart. However, oceanic crust is denser than continental crust, so eventually it begins to sink back into the mantle through subduction zones, causing the ocean basin to shrink and bringing the continental fragments back together again. The final stage occurs when the ocean completely closes and the continents collide, creating massive mountain ranges and welding the fragments together into a new supercontinent. This newly assembled landmass then becomes unstable due to heat buildup beneath it, and the cycle begins again with renewed rifting and breakup, ensuring that Earth's surface remains dynamic and ever-changing throughout geological time. Zircon crystals began forming within the first granitic rocks as they cooled and solidified from the global magma ocean. 13. Post-perovskite phase transitions in the deepest mantle. In the most extreme depths of Earth's interior, where pressures exceed 135 gigapascals and temperatures soar above 4,000 degrees Celsius, the very atoms within rock-forming minerals undergo dramatic structural reorganizations that fundamentally change how heat flows through our planet. These phase transitions involve the transformation of perovskite, the dominant mineral in the lower mantle, into an even denser crystal structure called post-perovskite. Understanding these deep Earth transformations helps scientists explain some of the most puzzling observations about how our planet's internal heat engine operates and influences surface geology. To grasp the significance of these phase transitions, imagine trying to compress a sponge until its internal structure completely reorganizes into a different arrangement. At the extreme conditions found in the lowermost mantle, the crystal structure of minerals becomes unstable and transforms into new arrangements that can better accommodate the crushing pressures. When perovskite transforms to post-perovskite, the atoms rearrange themselves into a more compact configuration, releasing energy and changing the physical properties of the rock. These phase transitions create a complex landscape of varying material properties at the base of the mantle, influencing how heat moves from the core toward the surface. The post-perovskite transformation occurs at depths between 2,500 and 2,800 kilometers below the surface, creating a zone where the thermal and mechanical properties of the mantle change abruptly. This transition zone may act as a thermal boundary layer that influences the formation of mantle plumes, the rising columns of hot rock that eventually reach the surface as volcanic hotspots. Recent high-pressure laboratory experiments and seismic observations have revealed that the post-perovskite transition is not uniform throughout the deep mantle. Instead, it creates a complex three-dimensional structure that varies with temperature and composition, helping to explain why seismic waves show such complex patterns of velocity variation in the deepest parts of our planet, connecting the extreme conditions of the deep Earth with the volcanic processes we observe at the surface. 14. Speleothem records of paleoclimate variability. Deep within limestone caves around the world, mineral formations called speleothems grow slowly over thousands of years, creating some of the most precisely dated and detailed records of past climate conditions available to scientists. These cave formations, including stalactites, stalagmites, and flowstones, form as groundwater saturated with dissolved calcium carbonate drips through cave systems, depositing thin layers of calcite that preserve chemical signatures of the environmental conditions that existed when each layer formed. Understanding how these formations encode climate information allows researchers to reconstruct rainfall patterns, temperature variations, and atmospheric conditions with remarkable precision across timescales ranging from seasons to hundreds of thousands of years. Think of speleothems as nature's own climate recording devices, where each microscopic layer represents a moment in environmental history frozen in stone. As rainwater infiltrates through soil and bedrock above caves, it dissolves carbon dioxide and becomes slightly acidic, allowing it to dissolve limestone and become saturated with calcium and carbonate ions. When this mineral-rich water enters the cave environment and encounters the different temperature and pressure conditions underground, it begins depositing calcite in thin, concentric layers that build up over geological time. The chemical composition of each growth layer reflects the environmental conditions at the surface when that water originally fell as precipitation. Oxygen isotope ratios within the calcite provide direct indicators of temperature and rainfall intensity, while trace elements like magnesium and strontium respond to seasonal changes in groundwater chemistry. The growth rate of speleothems also varies with climate conditions, creating visible banding patterns that can be counted like tree rings to establish precise chronologies. What makes speleothem records particularly valuable is their ability to be dated with extraordinary precision using uranium-thorium dating techniques, often providing age estimates accurate to within a few years, even for samples tens of thousands of years old. These cave archives have revealed detailed records of monsoon variability, ice age climate fluctuations, and rapid climate transitions that help scientists understand the sensitivity and stability of Earth's climate system. 15. The discovery of methane hydrate deposits. Beneath the seafloor and within Arctic permafrost regions lies a vast reservoir of frozen natural gas that contains more carbon than all known conventional fossil fuel deposits combined. These methane hydrate deposits, also known as gas hydrates or fire ice, consist of methane molecules trapped within cages of frozen water molecules, creating a crystalline solid that remains stable only under specific conditions of high pressure and low temperature. Understanding these enigmatic deposits has profound implications for energy resources, climate change, and the stability of continental margins around the world. Picture methane hydrates as nature's own storage containers, where individual methane molecules become locked within geometric cages, made of water molecules arranged in precise crystalline structures. These formations require the specific combination of cold temperatures and high pressures found in deep ocean, sediments, and permafrost regions. Under these conditions, water molecules organize themselves into polyhedral cages that can accommodate gas molecules, creating a solid material that looks remarkably similar to ice, but burns when ignited. Due to its high methane content, the formation of methane hydrates begins when organic matter in marine sediments undergoes bacterial decomposition in oxygen-poor environments, producing methane gas as a metabolic byproduct. This biogenic methane migrates upward through sediment layers until it encounters the stability zone, where temperature and pressure conditions favor hydrate formation. The methane becomes incorporated into the hydrate crystal structure, effectively removing it from the dissolved phase and concentrating it in solid form within the sediment. Current estimates suggest that global methane hydrate deposits may contain between 10,000 and 11,000 gigatons of carbon, representing an enormous potential energy resource but also a significant climate concern. Changes in ocean temperature or sea level could destabilize these deposits, releasing large quantities of methane into the atmosphere and potentially amplifying greenhouse warming. Understanding the stability and distribution of these deposits is crucial for geological discoveries. 7, 8, 9, 10, 11, and 12. Sleep documentary script. 16. Ancient magnetic field reversals recorded in rock. Throughout Earth's geological history, our planet's magnetic field has undergone hundreds of complete reversals, with magnetic north and south poles switching positions in a process that typically unfolds over several thousand years. These dramatic changes in Earth's magnetic behavior are permanently recorded in volcanic rocks and sediments that preserve the direction and intensity of ancient magnetic fields, like fossilized compass needles frozen in stone. Understanding these paleomagnetic records helps scientists reconstruct the history of Earth's magnetic field and provides insights into the complex processes occurring within our planet's molten iron core that generates this invisible shield, protecting us from harmful cosmic radiation. Imagine Earth's magnetic field as a vast invisible bubble surrounding our planet, generated by the motion of liquid iron within the outer core, some 3,000 kilometers beneath our feet. This geomagnetic field acts like a planetary compass, with field lines extending from the magnetic South Pole, arcing through space, and returning to the magnetic North Pole. The field's strength and direction at any location on Earth's surface depend on the complex patterns of convection and electrical currents flowing within the liquid iron core. When volcanic rocks cool from molten lava, iron-bearing minerals within them become magnetized in the direction of the existing magnetic field, creating a permanent record of the field's orientation at the time of cooling. Similarly, sedimentary rocks preserve magnetic records as iron-rich particles settling through water or air align themselves with the ambient magnetic field before becoming locked in place by burial and compaction. These natural recording systems have documented hundreds of magnetic reversals over the past several 100 million years. Magnetic field reversals occur when the convection patterns within Earth's outer core undergo major reorganization, causing the magnetic poles to weaken, wander, and eventually flip to opposite positions. During reversal transitions, Earth's magnetic field becomes much weaker and more complex, potentially allowing increased cosmic radiation to reach the surface. 17. Deep crustal thrust systems and nappe formation. In the heart of great mountain ranges around the world, enormous sheets of rock called nappes have been thrust dozens of kilometers horizontally over underlying formations, creating some of the most spectacular geological structures visible on Earth's surface. These massive thrust systems form when tectonic forces compress and shorten the continental crust during mountain-building episodes, causing older rocks to override younger ones and creating complex geological relationships that initially puzzled early geologists. Understanding nappe formation helps scientists reconstruct the collision histories of continents and explains how mountain ranges achieve their towering heights through horizontal compression rather than simple vertical uplift. Think of nappe formation as nature, this way of accommodating the tremendous horizontal forces generated when continents collide and compress against each other. When two continental masses converge, the intervening crust cannot simply disappear, so it must be accommodated through folding, faulting, and large-scale overthrusting. As compression continues over millions of years, enormous sheets of rock become detached from their original positions and slide horizontally for tens of kilometers along low-angle thrust faults, creating the distinctive nappe structures observed in many mountain belts. The formation process begins deep within the crust, where intense pressure and elevated temperatures make rocks more ductile and prone to flowing rather than brittle fracturing. As tectonic forces continue to compress the region, this ductile lower crust begins to flow horizontally, while the more brittle upper crust breaks along thrust faults. The combination of ductile flow below and brittle faulting above allows enormous volumes of rock to be transported horizontally across the landscape, eventually emerging at the surface as nappe complexes. What makes nappes particularly fascinating to geologists is how they preserve evidence of ancient paleogeographic relationships. Rocks that originally formed hundreds of kilometers apart can end up stacked vertically in nappe sequences, providing direct evidence of the distances involved in continental collision processes. 18. Ice core records of ancient atmospheric composition. Trapped within the glacial ice sheets of Greenland and Antarctica lies an extraordinary archive of atmospheric history extending back hundreds of thousands of years. These frozen libraries preserve tiny bubbles of ancient air that contain direct samples of past atmospheres, allowing scientists to measure the exact concentrations of greenhouse gases, volcanic ash dust, and other atmospheric constituents that existed during different periods of Earth's climate history. Understanding how to read these ice core records provides unparalleled insights into natural climate variability and helps scientists place modern atmospheric changes within the broader context of Earth's long-term climate evolution. Picture each annual layer of ice accumulation as a page in a vast atmospheric history book, with winter and summer layers creating distinct banding patterns that can be counted like tree rings to establish precise chronologies. As snow falls and compresses into ice, it traps small pockets of atmospheric air between the ice crystals. Over thousands of years, these air pockets become isolated bubbles that preserve samples of the ancient atmosphere with remarkable fidelity. The ice itself also contains chemical signatures that reflect temperature, precipitation patterns, and atmospheric dust levels when each layer formed. The process of extracting climate information from ice cores requires sophisticated analytical techniques and careful interpretation. Scientists drill cylindrical cores through ice sheets, carefully preserving the delicate layering structure as they extract continuous records spanning hundreds of thousands of years. Laboratory analysis involves measuring the concentrations of carbon dioxide, methane, and other trace gases trapped in the air bubbles, as well as analyzing the oxygen isotope ratios in the ice that provide direct indicators of past temperatures. What makes ice core records particularly valuable for understanding climate change is their ability to reveal rapid transitions and the natural variability of the climate system. These records have documented abrupt climate changes that occurred within decades, massive volcanic eruptions that altered global climate for years, and the natural rhythms of ice age cycles. 19. Ultra-high pressure minerals from meteorite impacts. When massive asteroids collide with Earth at cosmic velocities, They create conditions of pressure and temperature so extreme that ordinary minerals transform into exotic crystal structures that cannot form under any other natural circumstances on our planet. These ultra-high pressure minerals found only within and around meteorite impact craters provide direct evidence of the incredible forces generated during these catastrophic events, while offering unique windows into the behavior of matter under conditions that normally exist only deep within planetary interiors. Understanding these impact-generated minerals helps scientists reconstruct the history of cosmic bombardment and reveals how violent collisions have shaped the evolution of planetary surfaces throughout the solar system. Consider what happens during a large meteorite impact as cosmic forces meet terrestrial matter in a collision of unimaginable violence. When an asteroid traveling at speeds of 20 to 70 kilometers per second strikes Earth's surface, it instantly generates pressures that can exceed 100 gigapascals and temperatures that rival the surface of the Sun. Under these extreme conditions, the crystal structures of common minerals become unstable and transform into much denser arrangements that can only exist under such intense pressure and temperature conditions. The most famous of these ultra-high pressure minerals is diamond, which forms when carbon-bearing materials undergo shock metamorphism during impact events. While most people associate diamonds with deep mantle conditions, impact diamonds represent a completely different formation mechanism that can transform graphite and other carbon compounds into diamond within microseconds. These impact diamonds are typically much smaller than geological diamonds and often contain distinctive features that reveal their violent origins. Other ultra-high pressure minerals found in impact craters include stishovite, a dense form of quartz that normally exists only at depths greater than 300 kilometers within Earth's mantle, and ringwoodite, an olivine polymorph that typically forms only within the transition zone between the upper and lower mantle. The presence of these minerals at Earth's surface provides unambiguous evidence of impact processes and helps scientists understand how shockwaves propagate through planetary materials during large collision events. 20. The formation of seamounts and ocean islands, rising from the abyssal depths of the ocean floor, like underwater mountains, seamounts and volcanic islands, represent some of Earth's most dramatic expressions of deep-seated geological processes that connect the planet's interior heat engine with its surface topography. These isolated volcanic edifices form through hotspot volcanism, where columns of hot rock rise from deep within the mantle and eventually reach the seafloor to create massive volcanic constructions that can tower several kilometers above the surrounding ocean floor. Understanding how seamounts and ocean islands form helps scientists trace the motion of tectonic plates through geological time and provides insights into the thermal and chemical evolution of Earth's deep interior. Think of hotspot volcanism as Earth's way of releasing internal heat through focused points of volcanic activity that remain relatively stationary, while tectonic plates move across them, like conveyor belts. As an oceanic plate drifts over a mantle hotspot, the rising column of hot rock melts through the overlying seafloor, creating a volcanic edifice that continues to grow as long as the hotspot remains active beneath it. When the plate motion eventually carries the volcano away from the hotspot, volcanic activity ceases, and the seamount begins a long process of subsidence and erosion. The Hawaiian island chain provides the classic example of hotspot volcanism in action, where the currently active Big Island sits directly above the Hawaiian hotspot, while older islands extend northwestward in a chain that records millions of years of Pacific plate motion. As each volcano moves away from the hotspot, it stops growing and begins to subside under its own weight, eventually sinking below sea level to become a drowned seamount. This process creates long linear chains of volcanic structures that trace the path of plate motion across stationary hotspots. Seamounts play crucial roles in ocean circulation and marine ecosystems, acting as underwater barriers that deflect deep ocean currents and create upwelling zones that bring nutrients to surface waters. Many seamounts support unique biological communities that have evolved in isolation, making them important centers of marine biodiversity and natural laboratories for studying evolution in island environments. 21. Bridgmanite, the most abundant mineral you have never heard of deep within Earth's lower mantle under pressures more than 1,000,000 times greater than atmospheric pressure at sea level. Exists a mineral so common that it likely comprises more than 40% of our entire planet by volume. yet remained unknown to science until recent decades due to the extreme conditions required for its stability. This mineral, called bitumenite, represents the hypershear form of perovskite and dominates the mineralogy of Earth's interior between depths of approximately 700 kilometers below the surface. Understanding bitumenite helps scientists model how heat flows through Earth's deep interior and explains many of the seismic properties observed in the lower mantle. To appreciate the significance of bitumenite, we must first understand the extreme environment where it exists. At the pressures found in the lower mantle starting at about 24 gigapascals and increasing to 135 gigapascals at the core mantle boundary, the familiar minerals that exist near Earth's surface become completely unstable and transform into much denser crystal structures. Bitumenite forms when the common upper mantle minerals, olivine and pyroxene, undergo these pressure-induced phase transformations, reorganizing their atomic structures to accommodate the crushing conditions of the deep Earth. The crystal structure of bitumenite consists of silicon and oxygen, atoms arranged in interconnected octahedra and dodecahedra, with magnesium and iron atoms occupying specific sites within this framework. This arrangement creates a remarkably stable structure that can accommodate significant amounts of aluminum, calcium, and other elements that influence the physical and chemical properties of the lower mantle. The ability of bitumenite to incorporate these various elements helps control the distribution of chemical components throughout Earth's interior and influences the formation of chemically distinct reservoirs that may persist for billions of years. Recent hypershear laboratory experiments have revealed that bitumenite exhibits complex behavior under the temperature and pressure conditions of the lower mantle, including possible electronic transitions that could affect its ability to conduct heat and electricity, potentially influencing the dynamics of mantle convection and the generation of Earth's magnetic field. 22. Deep-time climate oscillations in ocean sediments. Buried within the layered sediments of the deep ocean floor lies a remarkable record of Earth's climate history that extends back hundreds of millions of years, preserving evidence of long-term climate oscillations that operate on timescales far beyond human experience. These marine sedimentary archives document the rhythmic expansion and contraction of ice sheets, the periodic warming and cooling of ocean waters, and the cyclical changes in atmospheric composition that have driven climate variability throughout Earth's geological past. Understanding these deep-time climate records helps scientists place modern climate change within the broader context of natural variability and reveals the fundamental connections between astronomical forcing, ocean circulation, and global climate systems. Think of deep ocean sediments as nature's most comprehensive climate library, where each microscopic layer represents a moment in Earth's environmental history, preserved in stone. As marine organisms die and settle to the seafloor, they create continuous sedimentary sequences that accumulate at rates of just a few centimeters per thousand years. Within these sediments, the fossilized shells of microscopic organisms called foraminifera preserve chemical signatures that directly reflect the temperature, salinity, and nutrient content of ancient seawater, creating detailed records of past ocean conditions. The most prominent climate oscillations recorded in marine sediments are the Milankovitch cycles, driven by predictable changes in Earth's orbital geometry around the Sun. These astronomical cycles operate on time scales of approximately 20,000, 40,000, and 100,000 years, corresponding to changes in the precession of Earth's rotational axis, variations in the tilt of the axis, and changes in the eccentricity of Earth's orbit. These orbital variations alter the distribution and intensity of solar radiation reaching different parts of Earth's surface, triggering the growth and decay of continental ice sheets and driving the familiar Ice Age cycles of the past 2 million years. Beyond the well-known Ice Age cycles, marine sediments reveal longer-term climate oscillations operating on million-year timescales, reflecting the complex interactions between tectonic processes, ocean circulation patterns, and atmospheric composition that shape Earth's long-term climate evolution and provide crucial insights into the natural variability of our climate system. 23. The role of fluids in deep metamorphic processes. Far beneath mountain ranges and within the roots of ancient continental crust, water and other fluids play crucial roles in transforming solid rock through processes that operate at temperatures and pressures that would instantly vaporize any surface water we know. These deep crustal fluids, derived from dehydration reactions, magmatic intrusions, and deeply circulating groundwater, facilitate chemical reactions, enable mineral transformations, and influence the mechanical behavior of rocks under conditions where normal surface processes cannot operate. Understanding the role of fluids in deep metamorphic processes helps scientists explain how continents evolve through geological time and reveals the complex chemical exchanges that occur between different reservoirs within Earth's crust. Picture deep metamorphic processes as a slow-motion chemical laboratory, where water acts as both a catalyst and a transport medium for elements that reorganize themselves into new mineral assemblages. At depths of 20 to 40 kilometers below the surface, where temperatures reach 500 to 800 degrees Celsius and pressures exceed 1 G, water exists in a supercritical state where it behaves very differently from liquid water at Earth's surface. Under these extreme conditions, supercritical water becomes highly reactive and capable of dissolving and transporting elements that would remain immobile under surface conditions. These deep fluids originate from several sources within the metamorphic environment. As sedimentary rocks undergo burial and heating, clay minerals and other hydrated phases release water through dehydration reactions that fundamentally change their crystal structures. Simultaneously, magmatic intrusions introduce additional fluids and heat into the surrounding rocks, while deeply circulating groundwater may penetrate to significant depths along fracture systems. The interaction between these different fluid sources creates complex chemical environments where elements can migrate, concentrate, and precipitate as new minerals. The presence of fluids dramatically accelerates metamorphic reactions by facilitating the transport of ions between mineral grains, enabling the growth of new minerals that would otherwise form extremely slowly or not at all. Fluids also influence the mechanical behavior of rocks by reducing friction along grain boundaries and fault surfaces, potentially triggering earthquakes and enabling large-scale deformation processes that shape mountain belts and contribute to the ongoing evolution of continental crust through deep time. 24. Varved lake sediments and annual climate cycles. In certain lakes around the world, sediments accumulate in precisely defined annual layers called varves that preserve extraordinarily detailed records of seasonal climate variations with resolution comparable to tree rings, but extending much further back in time. These remarkable sedimentary archives form when lakes experience pronounced seasonal contrasts in temperature, precipitation, and biological productivity that create distinct layers representing summer and winter deposition. Understanding varved lake sediments provides scientists with some of the highest resolution paleoclimate records available, revealing year-to-year climate variability and extreme events that occurred thousands of years before human instrumental records began. Think of varved lake sediments as nature's own calendar pages, where each pair of light and dark layers represents one complete annual cycle preserved in remarkable detail on the lake bottom. During summer months, increased biological productivity fills the lake with algae and other organisms, while higher temperatures and rainfall increase the delivery of organic matter and fine sediments from the surrounding watershed. These summer conditions typically produce lighter-colored layers, rich in organic matter and fine-grained minerals. Winter brings reduced biological activity and the cessation of most sediment input, creating darker layers composed primarily of fine clay particles that settled slowly through the cold, relatively still water. The formation of well-preserved varves requires specific environmental conditions that prevent the annual layers from being destroyed by bioturbation or physical mixing. Deep lakes with oxygen-poor bottom waters create ideal preservation environments because the lack of dissolved oxygen prevents bottom-dwelling organisms from burrowing through the sediments and disturbing the delicate layering. Additionally, lakes that are permanently or seasonally ice-covered often develop the thermal stratification necessary to maintain distinct seasonal deposition patterns. What makes varved records particularly valuable to climate scientists is their ability to capture short-term climate variability and extreme events with annual precision. These records have revealed the timing and magnitude of individual volcanic eruptions, documented the frequency and intensity of droughts and floods, and preserved evidence of rapid climate transitions that occurred over periods of just a few years, providing crucial insights into the natural variability and sensitivity of regional climate systems. 25. Iron snow formation in Earth's outer core. deep within Earth's molten outer core, under conditions of extreme pressure and temperature that exceed anything found elsewhere on our planet. A remarkable process occurs that resembles snowfall in a landscape made entirely of liquid metal. This iron snow forms when the liquid iron alloy that comprises the outer core becomes supersaturated with lighter elements and begins to precipitate solid iron crystals that slowly sink toward the inner core boundary. Understanding this exotic form of precipitation helps scientists explain some of the most puzzling observations about Earth's magnetic field generation and reveals how our planet's core has evolved through geological time. To visualize iron snow formation, imagine a vast ocean of molten metal existing at temperatures around 4,000 degrees Celsius and pressures more than 3 million times greater than atmospheric pressure at sea level. Within this liquid iron environment, lighter elements such as sulfur, oxygen, and silicon remain dissolved in the metallic alloy, much like salt dissolved in water. However, as the liquid metal cools and convects within the outer core, local conditions can arise where the solubility limits for these light elements are exceeded, causing pure iron to crystallize out of solution like snowflakes forming in a supersaturated atmospheric cloud. These iron snow crystals are fundamentally different from any precipitation we observe at Earth's surface. Each crystal consists of pure iron organized in a cubic crystal structure that remains stable under the extreme conditions of the outer core. As these metallic snowflakes form, they become denser than the surrounding liquid alloy and begin to sink slowly through the convecting outer core toward the inner core boundary. This process removes pure iron from the liquid outer core while concentrating the lighter alloying elements in the remaining liquid, gradually changing the composition and properties of the outer core through geological time. The formation and sinking of iron snow may play important roles in generating Earth's magnetic field by driving compositional convection within the outer core. As the iron crystals sink and release latent heat, they create buoyancy forces that contribute to the complex convection patterns responsible for generating the electrical currents that produce our planet's magnetic field, connecting this exotic deep Earth process to the magnetic shield that protects life at the surface. 26. Life in deep crustal fracture systems. Hidden within the fractured bedrock miles beneath Earth's surface exists a vast subsurface biosphere where microorganisms thrive in complete darkness, deriving energy from chemical reactions with surrounding rocks rather than sunlight. These deep crustal ecosystems represent some of the most extreme environments on our planet, where life persists at temperatures approaching the upper limits of biological tolerance and in the complete absence of photosynthetic energy sources that power surface ecosystems. Understanding these deep biosphere communities helps scientists explore the limits of life on Earth and provides insights into the possibility of life existing in similar extreme environments on other planets. Picture the deep continental crust as a three-dimensional maze of interconnected fractures and pore spaces where groundwater flows slowly through solid rock, creating hidden corridors where microscopic life can establish itself in perpetual darkness. These subsurface environments exist at depths ranging from hundreds of meters to several kilometers below the surface, where temperatures can exceed 80 degrees Celsius and pressures reach hundreds of times atmospheric pressure. Despite these extreme conditions, diverse communities of bacteria and archaea have adapted to thrive in these challenging environments, creating ecosystems that operate according to fundamentally different principles than surface life. The organisms that inhabit these deep crustal fracture systems derive energy through chemosynthetic processes that extract chemical energy from interactions between water and rock minerals. Some species obtain energy by oxidizing sulfur compounds, while others generate energy through the reduction of iron oxides or the fermentation of organic compounds that have seeped down from surface environments over geological timescales. These chemical energy sources support food webs that can persist for millions of years in complete isolation from surface ecosystems, creating biological communities that may be among the oldest continuously operating ecosystems on Earth. Recent discoveries have revealed that these deep biosphere communities may contain more biomass than all surface ecosystems combined, fundamentally changing our understanding of where life exists on our planet and demonstrating that the habitable zone extends far deeper into Earth's crust than previously imagined, with profound implications for understanding life's distribution throughout the solar system and beyond. 27. Extensional core complex formation. In regions where Earth's continental crust undergoes extension and stretching, extraordinary geological structures called metamorphic core complexes form through processes that bring rocks from depths of 20 to 30 kilometers to Earth's surface, while simultaneously creating some of the most spectacular mountain ranges and valley systems on our planet. These extensional structures develop when tectonic forces pull the crust apart, causing it to thin and allowing deep crustal rocks to flow upward and be exposed at the surface through a combination of faulting, uplift, and erosion. Understanding core complex formation helps scientists explain how continents respond to extensional stress and reveals the complex relationships between deep crustal processes and surface topography. Think of extensional core complex formation as nature's way of turning the continental crust inside out, bringing rocks that formed at great depth to the surface, while creating dramatic topographic relief in the process. When regional extension begins, the continental crust starts to stretch and thin like taffy being pulled apart. As this stretching continues, the upper brittle crust breaks along normal faults that dip at moderate to steep angles, while the deeper ductile crust responds by flowing plastically upward to fill the space created by extension. This upward flow of deep crustal material creates large dome-like structures where metamorphic rocks that crystallized at depth become exposed at Earth's surface. These metamorphic core complexes are typically bounded by low-angle detachment faults that separate the uplifted core of deep crustal rocks from the overlying brittle rocks that have been stretched and faulted during extension. The movement along these detachment faults can amount to tens of kilometers, representing some of the largest fault displacements documented anywhere on Earth. The rocks within metamorphic core complexes preserve detailed records of the pressure and temperature conditions that existed during their formation at depth, providing direct windows into processes that normally occur far beneath Earth's surface. These exposures allow geologists to study deep crustal processes directly and understand how heat, fluids, and deformation interact to modify continental crust during extensional events, revealing the complex feedbacks between mechanical, thermal, and chemical processes that shape the evolution of continental lithosphere through geological time. 28. Tree ring data extending back thousands of years. Within the cellular structure of ancient trees lies one of Earth's most precise and detailed archives of past environmental conditions, preserved in the annual growth rings that trees add each year throughout their lives. These tree ring records, called dendrochronological data, extend our understanding of climate, atmospheric conditions, and environmental change back thousands of years with annual precision that surpasses almost any other natural recording system. Understanding how trees encode environmental information in their growth rings helps scientists reconstruct past climates and reveals how ecosystems have responded to natural climate variations long before human industrial activity began to influence global environmental systems. Picture a tree as nature's own data logger, faithfully recording environmental conditions year after year in concentric rings of wood tissue that grow beneath the bark. Each spring, as temperatures warm and moisture becomes available, trees begin producing new wood cells that are typically larger and thinner-walled to accommodate the rapid transport of water and nutrients needed for vigorous growth. As the growing season progresses into summer and autumn, the tree produces smaller, thicker-walled cells that provide structural support as growth slows. This annual cycle creates the distinctive light and dark banding pattern we observe in tree rings, with each complete light-dark couplet representing 1 year of growth. The width, cellular structure, and chemical composition of each annual ring reflects the specific environmental conditions that tree experienced during that particular growing season. In years with abundant moisture and favorable temperatures, trees produce wide rings with large, numerous cells. During drought years or periods of environmental stress, trees form narrow rings with smaller cells and denser wood structure. Trees also respond to atmospheric chemistry changes, volcanic eruptions that reduce sunlight, insect outbreaks, and even major forest fires by producing distinctive ring patterns that can be identified decades or centuries later. The most remarkable aspect of dendrochronological records is their ability to extend continuously back in time, through the careful cross-matching of ring patterns from living trees with those from progressively older deadwood specimens. Ancient wooden beams from historical structures, subfossil logs preserved in lakes and bogs, and even petrified wood can be precisely dated and incorporated into master chronologies that now extend back over 10,000 years in some regions. These records provide annual resolution information about past climate conditions that helps scientists understand natural climate variability and provides crucial context for evaluating modern climate change within the broader perspective of Earth's environmental history. 29. The mysterious D-double prime layer. Deep within Earth's interior, just above the core mantle boundary at depths of approximately 700 kilometers below the surface, seismic waves reveal the existence of an enigmatic layer that represents one of the most complex and poorly understood regions of our planet's internal structure. This layer, designated as D-double prime by seismologists, exhibits unusual properties that suggest it plays crucial roles in mantle convection, heat transfer from the core, and the generation of mantle plumes that eventually create volcanic hotspots at Earth's surface. Understanding the D-double prime layer helps scientists comprehend the fundamental dynamics of heat and mass transfer within Earth's deep interior, and reveals how processes occurring thousands of kilometers beneath our feet influence geological phenomena we observe at the surface. To grasp the significance of the D-double prime layer, imagine it as a complex transition zone where the silicate rock of the lower mantle encounters the liquid iron alloy of Earth's outer core under conditions of extreme temperature and pressure that create unique physical and chemical environments. This layer experiences temperatures exceeding 3,000 degrees Celsius and pressures more than 1 million times greater than atmospheric pressure at sea level. Under these extreme conditions, minerals that make up the lower mantle undergo phase transitions and develop properties that are dramatically different from the same materials under less extreme conditions. Seismic studies reveal that the D-double prime layer has highly variable thickness, ranging from essentially absent in some regions to more than 300 kilometers thick in others, suggesting that it represents a dynamic boundary layer where thermal and chemical processes create complex three-dimensional structure. The layer exhibits unusual seismic wave velocities and shows evidence for strong lateral variations in physical properties that may reflect the presence of partially molten material chemical heterogeneities inherited from ancient subducted oceanic crust, or phase transitions in mantle minerals under extreme pressure and temperature conditions. Recent research suggests that the D-double prime layer may serve as a thermal and chemical boundary layer where heat from the core drives convective processes that eventually give rise to mantle plumes. These deep-seated thermal anomalies may incubate in the D-double prime layer for millions of years before rising through the mantle to create volcanic hotspots such as Hawaii, Iceland, and Yellowstone. The layer may also represent a repository for recycled crustal material that has been subducted deep into the mantle over geological time, creating chemical heterogeneities that influence the composition of volcanic rocks erupted at hotspot volcanoes and provide insights into the long-term chemical evolution of Earth's interior. 30. Abyssal plain sediment accumulation over millions of years. Across the vast expanses of deep ocean basins, far from the influences of continents and major ocean currents, sediments accumulate grain by grain on abyssal plains, through processes that operate continuously over millions of years to create some of Earth's most complete and undisturbed geological records. These deep ocean sedimentary sequences preserve detailed information about past ocean conditions, climate changes, biological productivity, and even extraterrestrial influences, such as asteroid impacts and cosmic dust accumulation. Understanding abyssal plain sedimentation helps scientists reconstruct Earth's environmental history and reveals how deep ocean basins serve as repositories for materials derived from atmospheric, oceanic, and even cosmic sources. Envision the abyssal plains as Earth's most patient and thorough archivists, collecting sedimentary particles that settle through several kilometers of water column to accumulate on the deep ocean floor at rates so slow that a single centimeter of sediment may represent hundreds or even thousands of years of deposition. These sediments come from diverse sources, including microscopic shells of marine organisms that lived in surface waters, fine clay particles eroded from continents and transported by ocean currents, volcanic ash from explosive eruptions, and even cosmic dust particles that continuously rain down from space. The dominant component of many abyssal plain sediments consists of microscopic shells and skeletons of planktonic organisms, such as foraminifera and coccolithophores that lived in surface waters and settled to the deep ocean floor after death. These biological remains, called biogenic oozes, preserve detailed chemical and isotopic records of surface ocean conditions, including temperature, salinity, and productivity. The abundance and species composition of these microscopic fossils also record how marine ecosystems responded to past climate changes, providing crucial insights into how ocean biological systems may respond to ongoing environmental changes. The extremely slow sedimentation rates and undisturbed depositional environments of abyssal plains create sedimentary sequences that preserve high-resolution records extending back tens of millions of years. These records have revealed the timing and magnitude of past climate transitions, documented the effects of asteroid impacts on ocean ecosystems, and provided evidence for cyclical climate changes driven by variations in Earth's orbital parameters. The study of abyssal plain sediments has fundamentally advanced our understanding of Earth system evolution by providing continuous high-resolution records of environmental change that extend far beyond the reach of terrestrial geological records, which are often interrupted by erosion and tectonic processes. 31. The Great Oxidation Event's Deep Earth Signatures. Approximately 2.4 billion years ago, Earth's atmosphere underwent one of the most dramatic chemical transformations in our planet's history when photosynthetic organisms began producing oxygen at rates that exceeded its consumption by chemical weathering and volcanic processes. This great oxidation event fundamentally altered not only atmospheric chemistry, but also created deep Earth signatures that are preserved in ancient rocks and continue to influence geological processes today. Understanding how this surface oxygenation event affected deep Earth systems helps scientists comprehend the profound connections between biological evolution, atmospheric chemistry, and solid Earth processes that have shaped our planet's evolution over geological time. Think of the Great Oxidation Event as a planetary-scale chemical revolution that began at Earth's surface, but sent shockwaves throughout the entire Earth system, creating changes that penetrated deep into the crust and upper mantle. Before this event, Earth's atmosphere contained virtually no free oxygen, and the oceans and atmosphere existed in a chemically reducing state where iron remained dissolved in seawater and sulfur compounds, dominated atmospheric chemistry. When cyanobacteria evolved the ability to produce oxygen through photosynthesis, this new oxidizing agent began to accumulate in the atmosphere and oceans, triggering a cascade of chemical reactions that transformed Earth's surface environment and created new pathways for chemical weathering and mineral formation. The deep Earth signatures of the Great Oxidation Event are preserved in several distinctive geological features that formed as oxygenated surface waters began to interact with crustal rocks in fundamentally new ways. Banded iron formations, which consist of alternating layers of iron oxides and silica, record the precipitation of dissolved iron from seawater as oxygen levels fluctuated during the transition period. Red beds, consisting of sandstones and mudstones, colored by oxidized iron minerals, document the emergence of oxygen-rich surface waters that could transport and deposit iron in oxidized form far from its source regions. Perhaps most significantly, the Great Oxidation Event initiated changes in crustal weathering processes that affected the long-term cycling of elements between Earth's surface and deep interior. The oxidation of sulfur-bearing minerals during weathering created new pathways for sulfur isotope fractionation that are recorded in sedimentary rocks and provide evidence for atmospheric oxygen levels throughout geological time. The event also enhanced the weathering of continental rocks and increased the flux of oxidized materials delivered to the deep Earth through subduction processes, gradually changing the oxidation state of the upper mantle and influencing the chemistry of volcanic gases released during subsequent magmatic activity, demonstrating how biological innovation can create geological consequences that persist for billions of years. 32. Deep-sea hydrothermal vent mineral gardens. In the perpetual darkness of deep ocean basins, where crushing pressures and near-freezing temperatures create some of Earth's most extreme environments, hydrothermal vents construct elaborate mineral edifices that rival the most spectacular geological formations found anywhere on our planet. These underwater mineral gardens grow through processes that combine extreme chemistry, physics, and biology to create structures that can reach heights of several stories, while supporting unique ecosystems that thrive in conditions previously thought to be incompatible with life. Understanding hydrothermal vent mineral formation helps scientists comprehend how chemical energy from Earth's interior can create and sustain complex geological and biological systems in the absence of sunlight. Picture these hydrothermal vents as underwater geysers that build their own elaborate architectural structures through the continuous precipitation of dissolved minerals from superheated water that emerges from beneath the seafloor. When seawater penetrates deep into oceanic crust through fracture networks, it encounters temperatures exceeding 400 degrees Celsius near cooling magma bodies beneath mid-ocean ridges. This extreme heating transforms the seawater into a powerful chemical solvent that leaches metals, sulfur, and other elements from the surrounding rocks, creating hydrothermal fluids that are dramatically different in composition from normal seawater. As these hot, mineral-rich fluids rise toward the seafloor and encounter the cold ocean water, rapid cooling triggers the precipitation of sulfide minerals that build up around the vent openings to create chimney-like structures. Different minerals precipitate in distinct temperature zones around each vent, creating structures with complex internal architecture and distinctive external morphologies. The hottest zones near vent openings are dominated by high-temperature minerals such as pyrite and chalcopyrite, while cooler regions further from active venting host lower-temperature minerals such as marcasite and barite. The most remarkable aspect of these mineral gardens is their role in supporting biological communities that derive energy entirely from chemical processes rather than photosynthesis. Chemosynthetic bacteria and archaea use the chemical energy available in hydrothermal fluids to produce organic compounds that support complex food webs, including giant tube worms, eyeless shrimp, and specialized crabs that have evolved to thrive in these extreme environments. The discovery of these ecosystems revolutionized our understanding of life's limits and revealed that biological communities can exist independently of solar energy, with profound implications for understanding the potential for life in similar environments on other worlds with subsurface oceans and hydrothermal activity. 33. The process of continental rifting and breakup. The gradual separation of continents represents one of Earth's most dramatic geological processes, unfolding over tens of millions of years as tectonic forces stretch and ultimately rupture continental lithosphere to create new ocean basins. Continental rifting and breakup involve complex interactions between deep mantle processes, crustal mechanics, and surface volcanism that transform solid continental masses into separate land masses separated by growing oceans. Understanding continental breakup helps scientists comprehend how supercontinents form and disperse throughout Earth's history and reveals the fundamental mechanisms by which our planet's surface geography evolves over geological timescales. Imagine continental rifting as an extremely slow-motion process where immense tectonic forces gradually pull apart continental crust, like taffy being stretched, until it eventually breaks apart completely. The process typically begins when mantle upwelling or changes in plate motion create extensional stresses within continental lithosphere. These stresses initially manifest as broad zones of crustal thinning where normal faults accommodate the gradual extension of the continental crust. As extension continues over millions of years, the crust becomes progressively thinner and more fractured, creating rift valleys that can extend for hundreds of kilometers across the continental surface. During the early stages of continental rifting, volcanic activity often becomes concentrated along the rift axis, as crustal thinning allows mantle-derived magmas to reach the surface more easily. This rift volcanism produces distinctive basaltic lava flows and intrusive rocks that record the progressive evolution of the rifting process. As the continental crust continues to thin and stretch, it eventually reaches a critical point where it can no longer support its own weight, leading to the formation of a narrow zone of highly extended crust that becomes increasingly vulnerable to complete rupture. The final stage of continental breakup occurs when the stretched continental crust finally ruptures completely, allowing seawater to flood into the newly formed rift valley and initiating the formation of a new ocean basin. At this point, seafloor spreading begins as new oceanic crust forms along a mid-ocean ridge system that develops within the former continental rift zone. The transition from continental rifting to oceanic spreading creates distinctive geological signatures that are preserved in the geological record, including sequences of rift-related volcanic rocks, fault systems that record the extensional deformation, and sedimentary deposits that document the environmental changes associated with the transition from continental to marine environments. These geological archives allow scientists to reconstruct past episodes of continental breakup and understand how the configuration of continents and oceans has evolved throughout Earth's history. 34. Pollen records preserved in deep sediment cores. Within the layered sediments that accumulate at the bottoms of lakes, bogs, and marine basins, microscopic pollen grains create detailed archives of past vegetation changes that extend back hundreds of thousands of years with remarkable precision and completeness. These palynological records preserve information about how plant communities responded to past climate changes, human activities, and natural disturbances, providing crucial insights into ecosystem dynamics and environmental change that cannot be obtained from any other source. Understanding how pollen records form and how they can be interpreted helps scientists reconstruct past environmental conditions and predict how ecosystems might respond to ongoing climate change. Think of pollen grains as nature's most durable messengers, carrying detailed information about past vegetation across landscapes and through time in protective shells that can survive for hundreds of thousands of years in sedimentary environments. Each year during flowering seasons, plants release enormous quantities of pollen into the atmosphere, where wind currents transport these microscopic reproductive structures across great distances before they settle into lakes, wetlands, and other depositional environments. The distinctive shapes, sizes, and surface textures of pollen grains allow scientists to identify them to specific plant families, genera, or even species, creating detailed inventories of past vegetation that can be precisely dated using radiocarbon and other geochronological techniques. The preservation of pollen in sedimentary sequences occurs because the outer walls of pollen grains are composed of sporopollenin, one of the most chemically resistant organic compounds known in nature. This remarkable substance allows pollen grains to survive burial, chemical weathering, and even moderate heating, while retaining their diagnostic morphological features. When sediment cores are extracted from lakes or marine environments, the pollen grains can be separated from surrounding sediment using chemical and physical techniques, identified under high-powered microscopes, and counted to reconstruct the relative abundance of different plant types during each time period represented in the sedimentary sequence. Pollen records have revolutionized our understanding of how vegetation communities respond to climate change by revealing that plant species migrate individually rather than as intact communities during periods of environmental transition. These records have documented the detailed timing and geographic patterns of vegetation changes, following the retreat of ice sheets after the last glacial maximum, revealed how human agricultural activities have influenced natural vegetation over the past several thousand years, and provided crucial information about ecosystem resilience and vulnerability that helps inform conservation strategies and climate change adaptation planning. The global network of pollen records now provides one of the most comprehensive archives of terrestrial environmental change available to scientists studying long-term ecosystem dynamics.
35. Deep Earth, water reservoirs larger than all oceans. Combined. Hidden within the crystal structures of minerals deep in Earth's mantle exists a vast reservoir of water that dwarfs all surface water on our planet, fundamentally challenging our understanding of water's distribution and movement throughout Earth's interior. This deep water exists not as liquid but as hydrogen and oxygen atoms incorporated into the crystal lattice of mineral phases that can store enormous quantities of water within their atomic structures. Understanding these deep Earth water reservoirs helps scientists comprehend the global water cycle, mantle dynamics, and the long-term habitability of our planet by revealing how water cycles between Earth's surface and deep interior over geological timescales. To grasp the magnitude of deep Earth water storage, imagine that the familiar oceans, lakes, rivers, and groundwater that we see at Earth's surface represent only a tiny fraction of our planet's total water inventory, with the vast majority hidden within mineral structures hundreds of kilometers beneath our feet. The key to understanding this hidden reservoir lies in recognizing that certain minerals can incorporate water molecules or hydroxyl groups. directly into their crystal structures when they form under the extreme pressures that exist in Earth's deep interior. These hydrous minerals can contain several percent water by weights, and given the enormous volume of the mantle, even small water concentrations represent staggering absolute quantities. The primary mechanism for water storage in the deep earth involves the crystal structure of minerals such as wadsleyite and ring, which are high-pressure forms of olivine that dominate the transition zone between the upper and lower mantle at depths of 410 to 660 kilometers below the surface. These minerals can incorporate substantial amounts of water into their crystal structures through the substitution of hydroxyl groups for oxygen atoms, effectively storing water in a form that remains stable under the extreme pressure and temperature conditions of the deep mantle. Laboratory experiments and seismic observations suggest that the transition zone may contain enough water to fill the oceans several times over. The cycling of water between Earth's surface and deep interior occurs through subduction processes that carry hydrated oceanic crust and sediments deep into the mantle, where the water is released through metamorphic reactions and incorporated into mantle minerals. This water can later be returned to the surface through volcanic processes, when hydrous mantle rocks undergo partial melting, creating a deep water cycle that operates over millions of years and plays crucial roles in plate tectonics, mantle convection, and the long-term evolution of Earth's oceans and atmosphere. Recent discoveries of diamond inclusions containing water-bearing minerals from the transition zone provide direct evidence for these deep Earth water reservoirs and confirm theoretical predictions about water storage in planetary interiors. 36. Mineral replacement processes and throughout Earth's crust, chemical processes operating over thousands to millions of years can completely replace the original minerals and rocks while preserving their external crystal forms, creating geological structures called pseudomorphs that maintain the shape of original minerals while consisting of entirely different chemical compositions. These replacement processes occur when chemically reactive fluids percolate through rocks and dissolve unstable minerals, while simultaneously precipitating new minerals in the spaces formerly occupied by the original crystals. Understanding mineral replacement in pseudomorph formation helps geologists interpret complex geological histories and reveals how crustal rocks respond to changing chemical conditions through geological time. Picture mineral replacement as nature's equivalent of restoration work on a historical building, where original structural elements are carefully removed and replaced with new materials while maintaining the architectural integrity and appearance of the original structure. When hot chemically active fluids encounter minerals that are unstable under the new chemical conditions, they begin to dissolve the original mineral grain by grain, atom by atom, while simultaneously precipitating new mineral phases in the cavities left by This coupled dissolution precipitation process can completely transform the chemical composition of a rock while preserving delicate details of original crystal faces, internal textures, and even microscopic features. The formation of pseudomorphs requires a delicate balance between dissolution and precipitation rates. Allows the replacement process to maintain the structural integrity of the original crystal framework. If dissolution proceeds too rapidly compared to precipitation, the original crystal shape collapses and the replacement mineral forms irregular metal. However, when the rates are properly balanced, the replacement process can preserve remarkable detail, including crystal faces, twin boundaries, and even fluid inclusions from the original mineral, creating fossils of former mineral assemblies that provide crucial information about past geological conditions. Common examples of pseudomorphic replacement include the transformation of pyrite crystals into iron oxides during weathering, the replacement of wood by silica during fossilization processes, and the conversion of primary igneous minerals into secondary alteration products during hydrothermal metamorphism. These replacement processes play important roles in ore deposit formation, as circulating hydrothermal fluids can dissolve worthless minerals and replace them with valuable metals, creating concentrated ore deposits while preserving the textural evidence of original rock structures. The study of pseudomorphs and replacement textures allows geologists to decipher complex sequences of geological events and understand how crustal rocks evolve in response to changing temperature, pressure, and chemical conditions throughout their burial and exhumation histories. 37. Deep seismic reflection studies of crustal structure, using artificially generated seismic waves that can penetrate deep into Earth's crust and reflect off buried geological boundaries. Geologists have developed sophisticated techniques for imaging crustal structure with remarkable detail and precision. Deep seismic reflection profiling involves generating controlled seismic energy at Earth's surface and recording the reflected waves that return after bouncing off rock layers, fault zones, and other structural features buried tens of kilometers beneath the surface. These studies have revolutionized our understanding of crustal architecture and revealed complex, three-dimensional structures that control fundamental geological processes, including mountain building, basin formation, and resource distribution. Imagine deep seismic reflection as a sophisticated form of geological echolocation that allows scientists to see through solid rock and map the internal structure of Earth's crust with the same clarity that medical ultrasound reveals internal body structures. The process begins with generating controlled seismic energy using techniques ranging from explosive charges to specialized vibrating trucks that create precisely timed seismic pulses. These energy waves propagate downward through the crust and reflect off interfaces between different rock types' fault planes and other structural boundaries where changes in rock density or seismic velocity cause portions of the wave energy to return toward the surface. The reflected seismic waves are detected by arrays of sensitive seismometers positioned along survey lines that can extend for hundreds of kilometers across regions of geological interest. Computer processing of the recorded seismic data creates detailed, cross-sectional images that reveal the geometry and internal structure of crustal features including sedimentary basins, fault systems, igneous intrusions, and metamorphic core. The resolution of these seismic images can reveal structural details as small as tens of meters at depths of several kilometers, providing unprecedented views of geological features that would otherwise remain completely hidden beneath Earth's surface. Deep seismic reflection studies have led to numerous fundamental discoveries about crustal structure and evolution, including the recognition that major fault zones extend much deeper into the crust than previously imagined. The discovery of extensive magma bodies beneath volcanic systems and the identification of buried impact structures that record ancient asteroid and comet collisions. These studies have also provided crucial information for resource exploration by revealing the structural controls on petroleum and mineral deposits, demonstrating how advanced geophysical techniques can bridge the gaps between surface geological observations and the hidden three-dimensional architecture of Earth's crust that controls so many important geological and economic processes.
38. The discovery of polymetallic nodule fields, scattered across vast areas of deep ocean floors, particularly in the Pacific, Atlantic, and Indian Ocean basins, lie extensive fields of potato-shaped metallic concretions, called polymetallic nodules that represent one of the most unusual and economically significant mineral resources on our planet. These remarkable structures grow extremely slowly over millions of years through complex chemical processes that concentrate valuable metals including manganese, iron, copper, nickel, and cobalt from seawater and sediment, pore fluids. The discovery and study of polymetallic nodule fields has opened new perspectives on deep ocean chemistry, resource distribution, and the potential for deep-sea mining, while raising important questions about environmental protection in deep marine ecosystems. To understand polymetallic nodule formation, envision the deep ocean floor as a vast chemical laboratory where dissolved metals slowly precipitate from seawater and sediment. Pour waters around nucleation sites, such as shark teeth, fragments of volcanic rock, or pieces of organic debris. The nodules grow through accretionary processes similar to those that form pearls in oysters, with successive layers of metal oxides and hydroxides depositing around the central nucleus over periods ranging from hundreds of thousands to millions of years. Growth rates are extraordinarily slow, typically measuring only millimeters per million years, making these nodules some of the most slowly forming geological structures on Earth. The chemical composition of polymetallic nodules reflects the unique conditions of deep ocean environments where oxygen-rich bottom waters interact with metal-rich sediment, pore fluids under conditions of extreme pressure and near-freezing temperatures. Manganese and iron oxides form the primary mineral phases, but the nodules also contain significant concentrations of economically valuable metals that are extracted from seawater through complex sorption and precipitation processes. The precise chemical composition varies depending on local oceanographic conditions, sediment composition, and the specific combination of chemical processes operating at each nodule field location. The discovery of extensive polymetallic nodule fields has created both opportunities and challenges for society, as these deposits contain enormous reserves of metals that are essential for modern technology, including batteries, electronics, and renewable energy systems. However, the potential environmental impacts of deep-sea mining in these remote ecosystems remain poorly understood, and the extremely slow growth rates of the nodules mean that any mining activities would essentially be harvesting geological resources that took millions of years to form. Current research focuses on understanding the ecological role of nodule fields, developing environmentally sustainable extraction techniques, and establishing international frameworks for managing these unique deep ocean resources that exist in international waters beyond the jurisdiction of any single nation. 39. The deep carbon cycle and diamond formation. Deep within Earth's mantle, carbon follows pathways that connect surface processes with interior dynamics, through a complex cycle that operates over millions of years and occasionally produces one of nature's most prized materials. The deep carbon cycle involves the subduction of carbon-bearing materials from Earth's surface into the mantle, the storage and transport of carbon in high-pressure mineral phases, and the return of carbon to the surface through volcanic processes and diamond-bearing eruptions. Understanding this deep carbon cycle helps scientists comprehend how carbon moves between different Earth's reservoirs and reveals the conditions under which diamonds form in the deep mantle, before being transported to the surface through explosive volcanic eruptions. Picture the deep carbon cycle as a vast conveyor system that transports carbon between Earth's surface and interior through pathways that involve some of the most extreme conditions found anywhere in the solar system. The cycle begins when carbon-bearing materials such as limestone, organic matter, and carbonate sediments are carried deep into the mantle through subduction processes. As these materials descend to depths exceeding 150 kilometers, increasing temperature and pressure cause chemical reactions that release carbon dioxide or transform carbon into new mineral phases that can remain stable under mantle conditions. Deep in the mantle, carbon can exist in several forms, including diamond, graphite, carbonate minerals, and dissolved carbon in silicate melts, depending on local temperature, pressure, and chemical conditions. Diamond formation occurs in regions of the mantle where pressure exceeds approximately 45,000 times atmospheric pressure and temperatures range between 900 and 1,300 degrees Celsius. Under these extreme conditions, carbon atoms arrange themselves in the characteristic tetrahedral crystal structure that gives diamond its exceptional hardness and optical properties. Most natural diamonds form at depths between 150 and 800 kilometers below Earth's surface, primarily within stable regions of ancient continental lithosphere called cratons. The transport of diamonds to Earth's surface occurs through extremely rapid and violent volcanic eruptions called kimberlite eruptions that originate deep in the mantle and travel to the surface at velocities exceeding 100 kilometers per hour. These eruptions create narrow carrot-shaped volcanic pipes that cut through the entire thickness of continental crust and bring mantle-derived materials, including diamonds, to the surface before the extreme pressure release can cause the diamonds to revert to graphite. The deep carbon cycle also influences global climate through its control on atmospheric carbon dioxide concentrations, as volcanic outgassing returns mantle carbon to the atmosphere, while weathering and subduction processes remove atmospheric carbon and transport it back to the deep Earth, creating a feedback system that helps regulate Earth's long-term plating, clot, creating a fickle clogs. Create clots long for longs, creelen, clogs, clongs, grades, crowd, clowns, clogs, sex, quick, clogs, black log, wig clogger, quick, quit, cluff, will, spaff, fill, work, to how, and hor, a set to hack, whip, hat, without, tat, hap, at a hack, a hat, dot, lick, ack, at, go, back, at, work, cack, at the pool, good cab, defs, wicked, the kick, poet, plug, at, word, gasp, for the wiggly bit, poets, 40. Lowest deposits recording wind patterns through time. Across vast areas of Earth's continents, particularly in regions that experienced periglacial conditions during ice ages, thick deposits of wind-blown sediment called loess preserve detailed records of atmospheric circulation patterns, dust transport pathways, and environmental conditions that existed during past climatic periods. These fine-grained, highly uniform deposits accumulate when persistent wind systems transport dust particles across great distances and deposit them in areas where topographic barriers or vegetation changes cause the wind to lose its sediment-carrying capacity. Understanding loess formation and the environmental records preserved within these deposits helps scientists reconstruct past atmospheric circulation patterns and reveals how continental-scale wind systems have responded to major climate changes throughout the Quaternary period. To visualize loess formation, imagine the Earth's atmosphere during glacial periods as a vast dust transport system where strong, persistent winds pick up fine sediment from exposed glacial outwash plains, dried lakebeds, and sparsely vegetated landscapes, carrying this material across entire continents before depositing it in massive blankets that can reach thicknesses of several hundred meters. The dust particles that form loess deposits are predominantly composed of quartz and feldspar grains, ranging from 10 to 50 micrometers in diameter, a size range that is optimal for long-distance atmospheric transport while being small enough to remain suspended in air currents for extended periods. The accumulation of loess deposits occurs episodically, with the thickest and most extensive deposits forming during glacial periods, when enhanced temperature gradients between ice sheets and ice-free regions created powerful atmospheric circulation systems, capable of transporting enormous quantities of dust across continental distances. These glacial period loess deposits often contain evidence for multiple episodes of accumulation, separated by periods of soil formation, creating complex stratigraphic sequences that record the alternation between glacial and interglacial conditions throughout the Pleistocene epoch. The environmental information preserved in lower sequences includes detailed records of past wind directions and intensities based on grain size variations and sediment composition. Evidence for vegetation changes recorded in fossil pollen and organic matter content, and indicators of temperature and precipitation patterns based on the degree of post-depositional soil formation and chemical weathering. Some lower sequences also contain volcanic ash layers that provide precise age markers for correlation between different regions, and rare occurrences of preserved plant remains and land snail shells that provide direct evidence for past ecosystems and environmental conditions. These comprehensive environmental archives have proven invaluable for understanding how atmospheric circulation systems respond to major climate changes, and for testing computer models of past climate conditions against detailed geological records of environmental change. 41. Archean greenstone belts and early plate tectonics in some of Earth's oldest preserved crustal rocks, dating back more than 2.5 billion years to the Archean Eon. Distinctive geological terrains called greenstone belts preserve crucial evidence for the earliest forms of plate tectonic activity on our planet. These ancient volcanic and sedimentary sequences metamorphose to characteristic green-colored mineral assemblages that give them their name, represent fragments of Archean oceanic crust and primitive, volcanic arcs that were incorporated into early continental masses through processes that may have differed significantly from modern plate tectonics. Understanding Archean greenstone belts helps scientists reconstruct the earliest stages of crustal evolution and reveals how plate tectonic processes developed during Earth's youth, when the mantle was significantly hotter and crustal dynamics operated under fundamentally different conditions than those we observe today. Picture early Earth as a dynamic planet where intense heat from radioactive decay and residual accretionary energy drove vigorous mantle convection that created multiple small zones of crustal formation and destruction, rather than the large coherent tectonic plates that characterize modern Earth. Archean greenstone belts formed in these early oceanic environments where ultramafic and mafic volcanic rocks erupted onto the seafloor, creating thick sequences of pillow basalts, comacionates, and associated volcanic rocks that accumulated in primitive ocean basins. These volcanic sequences were interlayered with sedimentary rocks, including cherts, banded iron formations, and turbidites that record the chemical and physical conditions of Archean surface environments. The preservation of greenstone belts within Archean cratons required their incorporation into stable continental masses through processes of crustal thickening and collision that operated differently from modern mountain building events. The higher mantle temperatures of the Archean led to more extensive melting and the production of larger volumes of mafic and ultramafic matter, while the thinner lithosphere and more vigorous convection created smaller, more numerous zones of crustal formation and destruction. This resulted in a style of tectonics, sometimes called heat pipe tectonics, where vertical movements dominated over the horizontal motions that characterize modern plate boundaries. Greenstone belts contain some of Earth's oldest evidence for biological activity, including stromatolites and chemical signatures that suggest the presence of early life forms adapted to the high temperature, chemically reducing conditions of Archean surface environments. These ancient terrains also preserve records of early atmospheric and oceanic chemistry, including evidence for the gradual transition from a reducing to an oxidizing atmosphere that culminated in the Great Oxidation event. The study of greenstone belts has fundamentally shaped our understanding of early Earth evolution and continues to provide crucial insights into how plate tectonic processes developed, and how the early biosphere evolved in conjunction with changes in solid Earth dynamics during the first half of Earth's history. 42. The formation of transform fault systems. Along certain types of plate boundaries, lithospheric plates slide horizontally past each other rather than converging or diverging, creating transform fault systems that accommodate the lateral motion between plates through complex networks of fractures and shear zones. These transform boundaries develop where the geometry of plate motions requires lateral displacement to maintain kinematic compatibility between different segments of diverging or converging plate boundaries. Understanding transform fault formation helps scientists comprehend the three-dimensional nature of plate motions and reveals how Earth's lithosphere accommodates the complex, geometric constraints imposed by motion on a spherical surface. Envision transform fault systems as Earth. This way of resolving geometric problems created when rigid lithospheric plates move across the curved surface of a sphere, requiring zones of lateral motion to connect segments of other types of plate boundaries in kinematically consistent ways. The most familiar examples of transform faults are the fracture zones that offset mid-ocean ridge segments, where the lateral motion between ridge segments creates long linear zones of intense deformation that can extend for hundreds of kilometers across ocean basins. These oceanic transform faults develop because spreading ridges cannot maintain perfectly straight geometries across large distances, and the offset segments require connecting zones of lateral motion to maintain the overall pattern of seafloor spreading. Continental transform fault systems, such as the San Andreas Fault in California, develop where oblique plate motions, or changes in plate boundary orientation, require lateral displacement to accommodate the relative motion between adjacent lithospheric plates. These continental transforms often exhibit more complex geometries than their oceanic counterparts, because they must cut through heterogeneous continental crust with variable strength and structural orientations. The deformation is typically distributed across zones that can be tens of kilometers wide, and include multiple parallel fault strands, stepovers, and restraining bends that create local zones of compression or extension within the overall transform system. Transform fault systems generate distinctive types of seismic activity characterized by strike-slip earthquakes that can produce some of the most destructive ground motions experienced in populated areas. The study of transform fault mechanics has revealed important principles about how stress accumulates and is released in fault systems, including the role of fault segmentation, the development of geometric complexities that influence earthquake rupture patterns, and the long-term evolution of fault systems through multiple earthquake cycles. Transform faults also create distinctive topographic and geological features, including linear valleys, offset stream channels, and characteristic rock assemblages that preserve records of cumulative displacement over millions of years, providing crucial information about long-term plate motions and crustal deformation processes. 43. Isotopic records of ancient ocean temperature. Preserved within the microscopic shells of marine organisms that lived millions of years ago, lies one of the most precise and detailed archives of past ocean temperatures available to paleoclimatologists. These isotopic records are based on the temperature-dependent fractionation of oxygen isotopes that occurs when marine organisms construct their calcium carbonate shells from dissolved ions in seawater. Understanding how these isotopic paleothermometers work helps scientists reconstruct detailed histories of ocean temperature changes and reveals how marine environments have responded to past climate variations over timescales ranging from annual cycles to millions of years. The foundation of oxygen isotope paleothermometry lies in the observation that the ratio of oxygen 18 to oxygen 16 incorporated into calcium carbonate shells depends on both the temperature of the water in which the organism lived and the isotopic composition of that water. As water temperature increases, organisms preferentially incorporate more of the lighter oxygen 16 isotope into their shells, creating a systematic relationship between shell isotopic composition and water temperature that can be calibrated through laboratory experiments and observations of modern organisms. This relationship allows scientists to calculate past water temperatures from the isotopic composition of fossil shells with precision approaching 1 degree Celsius. The most commonly used organisms for isotopic paleothermometry are foraminifera, microscopic marine protists that secrete calcium carbonate shells and are abundantly preserved in marine sediments throughout the geological record. Different species of foraminifera live at different depths in the water column, allowing scientists to reconstruct temperature profiles throughout the ocean and distinguish between surface and deep water temperature changes. Benthic foraminifera that live on the seafloor provide records of deep ocean temperatures, while planktonic species that live in surface waters record sea surface temperatures and seasonal variations in upper ocean conditions. Isotopic paleothermometry has revolutionized our understanding of past climate changes by providing quantitative temperature records that reveal the magnitude and timing of major climate transitions throughout Earth's history. These records have documented the gradual cooling that led to the onset of major ice ages, revealed rapid climate changes associated with transitions between glacial and interglacial conditions, and provided evidence for past greenhouse periods when global temperatures were significantly warmer than today. The technique has also revealed important information about ocean circulation changes, including variations in the formation and circulation patterns of deep water masses that play crucial roles in global climate regulation. Modern applications of isotopic paleothermometry continue to provide crucial data for testing and improving climate models by extending our knowledge of natural climate variability far beyond the brief period of instrumental temperature records. 44. The discovery of natural superconducting minerals. In one of the most surprising discoveries in modern mineralogy, scientists have identified several naturally occurring minerals that exhibit superconducting properties under specific conditions of temperature, pressure, and chemical composition. These natural superconductors challenge our understanding of how exotic electronic properties can develop in geological environments and reveal unexpected connections between solid-state physics and earth science. Understanding natural superconducting minerals helps scientists explore the conditions under which these remarkable electronic properties can emerge in nature and provides insights into potential applications of superconducting materials in technology and industry. To appreciate the significance of natural superconductors, it's important to understand that superconductivity is a quantum mechanical phenomenon where materials lose all electrical resistance and exhibit perfect magnetic field exclusion when cooled below a critical temperature. Until recently, superconductivity was thought to be primarily a laboratory phenomenon requiring artificially synthesized materials and extreme conditions not found in natural geological environments. The discovery that certain minerals can exhibit superconducting properties under conditions that exist within Earth's crust has fundamentally changed our understanding of where and how these exotic electronic states can occur. The first confirmed natural superconductor was copperite, a copper sulfide mineral that exhibits superconducting properties at temperatures below 1.6 Kelvin under specific structural conditions. Subsequent research has identified superconducting properties in several other sulfide and telluride minerals, including certain forms of pyrite and chalcopyrite under high-pressure conditions. These discoveries suggest that superconducting properties may be more common in natural systems than previously imagined, particularly in environments where sulfide minerals experience high pressures and low temperatures, such as those found in certain types of ore deposits. The geological conditions that promote natural superconductivity appear to be related to specific combinations of crystal structure, chemical composition, and electronic configuration that can develop when sulfide minerals undergo pressure-induced phase transitions or chemical modifications through hydrothermal alteration processes. The critical temperatures for natural superconductors are generally much lower than those found in artificially synthesized high-temperature superconductors, but the discovery of these natural phenomena has provided new insights into the fundamental physics of superconducting states and has suggested new directions for materials. Research aimed at developing practical superconducting applications for energy transmission, magnetic levitation, and quantum computing technologies. 45. Deep ocean trench sedimentary processes. In the deepest parts of Earth's oceans, where oceanic lithosphere descends into subduction zones, sedimentary processes operate under extreme conditions that create some of the most complex and scientifically important depositional environments on our planet. These deep ocean trenches, which can reach depths exceeding 11 kilometers below sea level, serve as collection points for sediments derived from multiple sources and create unique depositional conditions that preserve detailed records of tectonic activity, climate change, and deep ocean dynamics. Understanding trench sedimentary processes helps scientists reconstruct the history of subduction zones and reveals how the deepest parts of the ocean system respond to tectonic and environmental changes. Picture deep ocean trenches as enormous sediment traps, where materials from throughout the ocean system converge and accumulate under conditions of extreme pressure, near freezing temperatures, and complete darkness. These trenches receive sediments from several sources, including fine-grained particles that settle through the entire water column from surface waters, turbidity currents that transport coarse sediments from continental margins, and materials eroded directly from the steep walls of the trench itself. The convergence of these different sediment sources creates complex depositional patterns that vary both temporally and spatially within individual trench systems. The extreme depths of ocean trenches create unique physical and chemical conditions that influence sedimentary processes in ways not observed in other marine environments. The immense pressure at these depths affects the compaction and diagenesis of sediments, while the isolation from surface processes creates environments where organic matter can be preserved under highly reducing conditions. Hydrothermal activity associated with the subduction process can also influence trench sedimentation through the introduction of chemically precipitated minerals and the alteration of existing sedimentary materials. Through fluid-rock interactions, trench sedimentary sequences preserve important records of subduction zone activity, including evidence for prehistoric earthquakes recorded as turbidite sequences, triggered by seismic shaking, variations in sediment supply related to climate-driven changes in continental erosion rates, and chemical signatures that reflect changes in hydrothermal activity associated with variations in subduction processes. These sedimentary archives also contain information about deep ocean circulation patterns, as the transport and deposition of fine-grained sediments in trenches is influenced by deep ocean currents that can vary in response to climate changes and tectonic reorganizations. The study of trench sedimentary processes has become increasingly important for understanding natural hazards associated with subduction zones, as sedimentary records can extend our knowledge of earthquake and tsunami frequency far beyond historical records and provide crucial information for assessing long-term seismic risks in coastal regions. 46. Snowball Earth episodes and their deep crustal records. During several periods in Earth's history, most recently between 750 and 580 million years ago, our planet experienced extreme glacial conditions, so severe that ice sheets may have extended from the poles to the equator, creating what geologists call snowball Earth episodes. These remarkable climatic events left distinctive signatures in the geological record that provide evidence for global-scale glaciation and reveal the complex feedbacks between climate, ocean chemistry, and biological evolution that characterize Earth's climate system. Understanding snowball Earth episodes and their crustal records helps scientists comprehend how Earth's climate system can undergo dramatic transitions and reveals the resilience of life under extreme environmental conditions. To envision a snowball Earth, imagine our planet as a giant ice ball where glacial ice extended from the polar regions to tropical latitudes, creating a global ice cover that dramatically increased Earth's reflectivity and created powerful positive feedbacks that maintained the frozen state for millions of years. These extreme glacial episodes were likely triggered by a combination of factors, including volcanic outgassing that reduced atmospheric carbon dioxide concentrations, continental configurations that promoted ice sheet formation, and biological processes that altered atmospheric composition through photosynthesis and organic carbon burial. The geological evidence for snowball Earth episodes comes from several distinctive rock types and sedimentary sequences that formed under the extreme conditions of global glaciation. Glacial deposits called diamictites, consisting of unsorted mixtures of fine and coarse sediment deposited directly by ice, are found in low-latitude locations where they provide evidence for ice sheets in tropical regions. These glacial deposits are often overlain by distinctive limestone and dolostone sequences, called cap carbonates, that formed when rapid deglaciation led to extreme greenhouse conditions and massive precipitation of carbonate minerals from supersaturated seawater. The deep crustal records of snowball Earth episodes include isotopic signatures that reflect the extreme disruption of global carbon and sulfur cycles during these events. Carbon isotope excursions in marine carbonates provide evidence for dramatic changes in oceanic productivity and carbon cycling, while sulfur isotope anomalies suggest that atmospheric oxygen levels may have fluctuated significantly during and after glacial episodes. These chemical signatures are preserved in sedimentary rocks worldwide and provide some of the strongest evidence for the global extent and environmental severity of snowball Earth conditions. The biological implications of snowball Earth episodes are profound, as these extreme environmental conditions may have driven evolutionary innovations that led to the emergence of complex multicellular life. The timing of the last snowball Earth episodes immediately precedes the appearance of the first complex multicellular fossils in the geological record, suggesting that the environmental stress created by global glaciation may have stimulated evolutionary processes that led to increased biological complexity and diversity. Modern research on snowball Earth episodes continues to provide insights into how Earth's climate system responds to extreme perturbations and helps scientists understand the potential for rapid climate transitions under conditions of strong environmental forcing. 47. Crustal delamination and lithospheric dripping. In certain tectonic environments, particularly beneath thickened continental crust, in mountain belts and volcanic plateaus, gravitational instabilities can develop that cause dense portions of the lithosphere to separate and sink into the underlying mantle through processes called delamination and lithospheric dripping. These dramatic examples of solid-state convection remove the lowermost parts of continental lithosphere and replace them with hot mantle material, creating profound changes in crustothermal structure, magmatic activity, and surface topography. Understanding delamination processes helps scientists explain rapid uplift events, unusual volcanic activity, and the long-term evolution of continental lithosphere in regions of crustal thickening and thermal weakening. Picture lithospheric delamination as a geological process similar to honey dripping from a spoon, where the dense lower portions of thickened continental lithosphere become gravitationally unstable and separate from the overlying crust to sink slowly into the mantle over periods of millions of years. This process typically occurs in regions where continental crust has been thickened through tectonic processes such as continental collision or volcanic loading, creating thick crustal sections where the dense, thick lower crust and underlying lithospheric mantle become gravitationally unstable relative to the underlying asthenosphere. The initiation of delamination requires specific conditions, including sufficient crustal thickness to create gravitational instability, thermal weakening of the lithosphere through magmatic processes or radioactive heating, and mechanical weakening through fluid infiltration or metamorphic reactions that reduce rock strength. Once these conditions are met, the dense lower lithosphere begins to founder and pull away from the overlying crust, creating a process that can accelerate as the sinking material heats up and becomes more ductile during its descent into the mantle. The surface manifestations of lithospheric delamination are dramatic and include rapid surface uplift, as the removal of dense lithosphere allows the remaining crust to rise isostatically. Intense volcanic activity, as hot mantle material replaces the delaminated lithosphere and generates large volumes of mafic magma, and changes in regional topography that can create new mountain ranges or modify existing ones. Delamination also produces distinctive geochemical signatures in volcanic rocks. including evidence for the interaction between crustal and magmas and isotopic signatures that reflect the involvement of recycled crustal materials in magma generation processes. The recognition of delamination as an important geological process has helped explain several puzzling observations about continental evolution, including rapid vertical motions in certain mountain belts, the occurrence of mafic volcanism in regions of thickened continental crust, and the development of high-elevation plateaus that seem to require more support than can be provided by crustal thickening alone. Modern research on delamination processes continues to reveal new aspects of how continental lithosphere evolves, and how gravitational and thermal processes interact to reshape the deep structure of continents over geological time. 48. Deep-sea forum shells recording ocean chemistry changes. Among the most valuable archives of past ocean conditions are the microscopic calcium carbonate shells of foraminifera, single-celled marine organisms whose fossilized remains preserve detailed chemical records of ancient seawater composition, temperature, and biological productivity. These tiny shells, many smaller than a grain of sand, incorporate trace elements and isotopic signatures from seawater during their formation, creating geochemical fingerprints that can be decoded millions of years later to reconstruct past ocean chemistry and environmental conditions. Understanding how foraminiferal shells record ocean chemistry helps scientists trace the evolution of marine environments and reveals how ocean systems have responded to major environmental changes throughout Earth's history. Think of foraminiferal shells as microscopic time capsules that capture and preserve the chemical essence of ancient seawater through the unincorporation of dissolved ions and trace elements during shell calcification. When foraminifera construct their shells, they extract calcium and carbonate ions from seawater and precipitate them as calcium carbonate crystals. But this process also incorporates small amounts of other dissolved constituents, including magnesium, strontium, barium, and various isotopes whose concentrations in the shell reflect their abundance in the surrounding seawater and the environmental conditions during shell formation. Different elements and isotopic systems preserved in foraminiferal shells provide information about different aspects of past ocean conditions. Magnesium-to-calcium ratios in shells reflect seawater temperature and can be used to reconstruct past sea surface and deep water temperatures with high precision. Strontium isotope ratios provide information about past rates of continental weathering and volcanic activity, as these processes control the isotopic composition of dissolved strontium in seawater. Boron isotopes record past ocean pH and atmospheric carbon dioxide levels, while trace elements such as zinc and cadmium provide information about past nutrient levels and biological productivity. The geographic distribution and ecological preferences of different foraminiferal species add another dimension to the environmental information preserved in their shells. Planktonic foraminifera that lived in surface waters provide records of surface ocean conditions and can be used to reconstruct past patterns of ocean circulation and productivity. Benthic species that lived on the seafloor record deep water conditions and can reveal changes in deep ocean circulation, oxygen levels, and the input of nutrients from continental sources. The seasonal and depth migrations of some species create additional complexity in the environmental signals preserved in their shells, but also provide opportunities to reconstruct detailed information about seasonal cycles and water column structure in ancient oceans. Foraminiferal geochemistry has revolutionized paleoceanography by providing quantitative records of past ocean conditions that span hundreds of millions of years, with temporal resolution approaching annual scales in some cases. These records have documented major transitions in Earth's climate system, revealed the timing and magnitude of past ocean acidification events, and provided crucial data for understanding how marine ecosystems respond to environmental change. The continued development of new analytical techniques and the discovery of additional geochemical proxies in foraminiferal shells promise to further expand our ability to reconstruct past ocean conditions and understand the complex interactions between climate, ocean chemistry, and marine life throughout Earth's history. 49. The discovery of the inner core, Earth's fifth layer. Recent advances in seismic imaging have revealed that Earth's solid inner core, long considered the deepest and most uniform part of our planet, actually contains an additional distinct layer that represents a fifth major division of Earth's internal structure. This innermost region, sometimes called the inner core, exhibits different seismic properties than the surrounding inner core and may represent a fundamental change in the crystal structure or composition of iron under the extreme conditions that exist at Earth's center. The discovery of this fifth layer has important implications for understanding planetary formation, core evolution, and the processes that generate Earth's magnetic field. To understand the significance of the inner core, it's essential to recognize that Earth's interior structure has been traditionally divided into four major layers: the crust, mantle, liquid, outer core, and solid. Inner core, each with distinct physical and chemical properties determined by pressure, temperature, and composition. The inner core, which extends from about 150 kilometers depth to Earth's center at 371 kilometers depth, was thought to consist of a relatively uniform sphere of solid iron-nickel alloy that crystallized from the liquid outer core as Earth cooled over geological time. The evidence for the inner core comes from detailed analysis of seismic waves that travel through Earth's center, particularly waves that make multiple passes through the inner core and can reveal subtle variations in seismic velocity and wave propagation characteristics. These studies have identified a spherical region within the innermost portion of the inner core, extending from about 5,800 kilometers depth to the center, where seismic waves behave differently than in the surrounding inner core material. The boundary between the inner core and inner core appears to be relatively sharp, suggesting a distinct change in physical properties rather than a gradual transition. The physical nature of the inner core remains uncertain, but several hypotheses have been proposed to explain its distinct seismic properties. One possibility is that the extreme pressure conditions at Earth's center cause iron to undergo a phase transition to a different crystal structure with altered seismic properties. Another hypothesis suggests that the inner core may have a different composition than the surrounding inner core, perhaps enriched in lighter elements or containing different proportions of iron and nickel. A third possibility is that the inner core represents the oldest part of Earth's solid core and preserves evidence of different crystallization conditions that existed during the early stages of core formation. The discovery of the inner core has important implications for understanding core dynamics and the generation of Earth's magnetic field, as the structure and properties of the solid inner core influence the convection patterns in the liquid outer core that produce the magnetic field. The existence of this additional layer also provides new constraints on models of planetary formation and evolution, as it suggests that the process of core formation and solidification may be more complex than previously thought. Ongoing research continues to refine our understanding of the inner core's properties and origin, using increasingly sophisticated seismic analysis techniques and high-pressure laboratory experiments to explore the behavior of iron under the extreme conditions that exist at Earth's center. 50. Salt dome formation and migration through geological time. Beneath many sedimentary basins around the world, particularly those containing petroleum resources, ancient deposits of salt flow slowly through overlying rock layers, like underground glaciers, creating dramatic geological structures called salt domes that can rise thousands of meters from their original depositional levels. This remarkable process occurs because salt behaves as a fluid over geological timescales, flowing upward through denser, overlying sediments under the influence of buoyancy forces and pressure gradients. Understanding salt dome formation and migration helps geologists locate petroleum resources, assess geological hazards, and comprehend how buried sedimentary layers can undergo large-scale deformation through solid-state flow processes. Imagine thick sequences of ancient salt deposits originally formed by the evaporation of seawater in arid basins millions of years ago as underground rivers of flowing rock that move slowly upward through overlying sedimentary layers at rates measured in millimeters per year. This process, called halokinesis, begins when thick salt layers become buried beneath younger sedimentary rocks that are denser than the salt. Because salt has a lower density than most sedimentary rocks and behaves as a viscous fluid over long time periods, it becomes gravitationally unstable and begins to flow upward wherever weaknesses in the overlying rocks provide pathways for movement. The upward migration of salt creates distinctive geological structures as the flowing salt encounters resistance from overlying rocks and finds pathways of least resistance through complex three-dimensional networks of fractures, fault systems, and zones of structural weakness. As salt continues to flow upward, it can form mushroom-shaped domes that penetrate through kilometers of overlying sedimentary rocks, creating circular or elongated surface expressions that can be detected through geological mapping and geophysical surveys. The flowing salt also creates complex deformation patterns in surrounding rocks, including folding, faulting, and tilting that can trap petroleum and create important economic resources. Salt domes create distinctive geological features both at the surface and in the subsurface that have important implications for natural resource exploration and geological hazard assessment. The upward flow of salt often brings up associated minerals and fluids that can form important ore deposits, including sulfur, petroleum, and various metal sulfides that precipitate around the margins of salt domes. However, salt domes can also create geological hazards, including ground subsidence when salt dissolves at shallow depths, structural instabilities that affect construction projects, and complex hydrogeological conditions that influence groundwater flow patterns. The study of salt tectonics has become increasingly important for petroleum exploration because the structural traps created by salt movement often contain significant hydrocarbon accumulations, and the thermal properties of salt affect the maturation of organic matter in surrounding rocks. Modern three-dimensional seismic imaging techniques allow geologists to map salt structures in remarkable detail, revealing complex networks of salt walls, overhangs, and interconnected flow systems that demonstrate the extraordinary mobility of buried salt deposits over geological time. These studies continue to reveal new aspects of how solid materials can flow and deform under natural conditions, providing insights that are relevant to understanding deformation processes in other geological settings, including glacial ice, magma chambers, and the deep mantle.